This is Mrs. Haslauer's video on proportions review and similar triangles. What you need to know by the end of the video is how do you solve a proportion. Again, that's review. We've already done some of this work this year. How you identify if objects are similar, and how you find the missing side length of a similar figure. So take out your note sheet and let's get started. We're going to do a quick review on our proportions. The first question asks, are the following ratios equivalent? What you need to do, how you figure out if any given ratio is equivalent, is if their cross products are the same, or if you can reduce them down into the exact same fraction. What I mean by that is, if I'm comparing the fraction 3/7 to 6/14, I can simplify them down, or I can cross multiply. If I cross multiply them, you're going to take 3 times 14, set it equal to 7 times 6 or 6 times 7. Again, the commutative property allows you to switch them around like that. And you get 42 equals 42. So the answer to that is yes. The ratios are equivalent. Over here we've got 5/8 and we're comparing that to 9/12. If you're good at reducing, you'll notice that 5/8 can, will stay 5/8. You can't reduce 5/8, but you can reduce 9/12 by 3, which turns into 3/4. Those do not reduce down to equivalent fractions, so they're not going to be equal to each other. But if we want to stick to cross multiplying, we're just going to do this quickly. 5 times 12 is 60, and 60, of course, does not equal 72. We're going to use that same idea of cross multiplying when we get to these proportions. A proportion is a special form of an algebraic equation. It is used to compare two ratios or make equivalent fractions. A ratio is a comparison between two values. And again, to solve your proportion, you're going to multiply the extremes and set them equal to the product of the means. In other words, we're just going to cross multiply. In this case, we're not asking if two ratios are the same or not. We're being told that they are the same, but we have to figure out what number will make this true. So it's still two fractions set equal. We're going to cross multiply. 3m equals 5 times 9. Now it turns into a very basic equation that we were all very good at. 9 times 5 is 45. The 3 and the m are connected by multiplication. To break multiplication, you divide, and you get m equals 15. So what this is saying is, every time I see an m, I plug in a 15. Now, does 3/9 equal 5/15? Well, if we want to reduce 3/9, you can divide by 3 and get a third. And if you want to reduce 5/15, divide by 5, you get 1/3 equals 1/3. And we did it correctly. So there's your value for m. This one's a little differently. You have a binomial in the denominator, but the good thing is it's still the same process. You have two fractions set equal, so you're just going to cross multiply. Hopefully you remember that when multiplying a monomial by a binomial, this is distribution. Do not get lazy and forget to put your parentheses around it. If you want to put your parentheses while it's still in fraction form, that would be okay too. 6 times 7 is 42 equals 2y, or you can still put your rainbows if that helps, and then 2 times -3 is -6. The y is attacking the 2. The -6 can escape by adding 6. 48 equals 2y. That gives you 0. Divide both sides by 2, and you get y equals 24. So that's our quick review on proportions and how to solve them. All right. If you have any questions, please do not hesitate to come see me tomorrow. And now we're going to use what we know about our proportions and apply it to our similar polygons. Similar polygons are figures that have exactly the same shape but not necessarily the same size. We saw this a lot when we did our dilations. Remember that by multiplying by a scale factor of either a whole number or a fraction, we're either making it bigger or smaller. It's very important that you understand this word corresponding. We're going to talk a lot about that in a couple minutes. Corresponding angles of two figures are in the same relative position, and corresponding sides are in the same relative position. They need to be the same figure. It's just either bigger or smaller. Two figures are similar if and only if. This is why this is bolded. It's very important. The lengths of corresponding sides are proportional, and all pairs of corresponding angles have equal measure. So the angles are all the same. The side lengths have to be in proportion. If they all don't grow or shrink at the same rate, there's no way you're going to have the same shape. So all three angles of a triangle are congruent, meaning you're corresponding, very important. And all three angles of the second triangle, then the triangles are similar. What I mean by that is, and you guys have seen this notation, but let's go over it quick. All I did is copy and paste ABC to make DEF, but then I made it a little bit bigger. So angle A has to be congruent to angle D because they're the same measurement. You're going to use your arc length, one arc to one arc. B will be congruent to E, so you're going to use two arc lengths. Now you need to be careful with that. You can't use one arc length or else you're saying that A is going to be equal to B, and that's not true. And then C, we're going to use three arc lengths, will be equal to F. All right, so similar figures, it's not saying that all the angles have to be the same. These obviously aren't. This isn't an equilateral triangle or an equal angular triangle. But the corresponding, meaning A corresponds to D, B corresponds to E, and C corresponds to F. Those are going to be equal to each other. They make a pair. So what I mean by notation is we have notation in geometry when we're looking at shapes to help us out so we don't have to write everything out. Once you get used to the notation, guys, it's super simple. You've already seen quite a bit of it, but now you're expected to use it. The symbol for angle is just like that. All right, it looks like an angle, it looks like an acute angle. Please don't overcomplicate it. So angle A is congruent, the equal sign with the squiggly over it, to angle D. There's one angle congruency statement. Then we've got angle B congruent to angle E, and angle C congruent to angle F. There's my notation for my angle length. Very important. That's part of proving that these two triangles are similar if their corresponding angles are the same. And now we got to talk about this corresponding sides are proportional. So important. It has to have the same scale factor, just like your dilations. They can't just grow or shrink at whatever rate they feel like, or else they're going to change the shape. Now be very careful when you're labeling these. All right, so you're going to go from one triangle to the other, but it's got to be the corresponding side length. So for example, if I'm going to look at AB, AB is the left side of the triangle. I'm going to compare the length of AB to the length of DE. Now be careful with the way you're ordering these. All right, A is the bottom corner up to B, which is the top. So when you're labeling for the corresponding side, D is in the bottom corner and E is at the top. You need to be very, very careful when you're labeling. Let's see, next angle or next side length. AC, so that's the bottom of my triangle going from left to right. That corresponds with DF. And last but not least, we've got BC, which is the top right, is going to correspond to EF. Right? Order does matter, so please pay attention to that. And I know we don't have numbers, but if we did, we could just replace them in for these side lengths, and everything would have to be the same because they'd all have to be the same scale factor. All right, so this is just basic notation. We got to get used to those symbols. Now let's actually practice with it. So here's my two triangles. I want to see if I want to look and see what they tell me. So in the diagram, triangle RST is similar. Very important. All right, we have to know. It's just a symbol that looks like this. This just means similar, not congruent, meaning one shape is bigger than the other, but they are similar. All their angles are the same, and all their sides are in proportion. They're telling you this already. We're going to list all the pairs of congruent angles. So all that we're being asked to do is find the corresponding angles. So we've got, you can start anywhere you want. So we got angle R would be congruent to angle, see how it's in the bottom left? Bottom left would be angle X. Angle S would be congruent to angle Y. And last but not least, we have angle T congruent to angle Z. Very important to remember, the angles are not similar. The angles are congruent. They have to be the exact same thing. The corresponding angles are the same. That's very, very important. Now, you're going to check that the ratios of corresponding side lengths are equal. It has to have the same scale factor. So what I mean by that is we're going to compare how each side either grew or shrank. How did 25 get to 15, 30 to 18, and 20 to 12? If they don't follow the exact same ratio, something went wrong and they're not similar. So I'm going to start by comparing RT to XZ. So that would be the ratio 25 over 15. We can reduce the top and the bottom by 5, and you get 5/3. So my ratio to go from 25 to 15 was to multiply by 5/3. Let's check the next side. If I started with the 25, which is RT, I got to keep to the same pattern. So now I'll just go over here, and I'm going to compare the side length of 30 to a side length of 18. Greatest common factor to reduce would be 6, and I would get 5/3 again. So far so good. We have the same ratio, the same scale factor of 5/3. And last but not least, I've got to compare 20 to 12. Reduce 20 and 12 by the GCF of 4. And again, you get 5/3. So because you get 5/3, which equals 5/3, which equals 5/3, we're good. All right, all the side lengths are in proportion. They all grew or shrank at the same rate. So that's your side lengths are in proportion. Write a statement of proportionality. Well, that's just talking about your actual side lengths, making it official. RT was compared to XC. So there was our first ratio. Then we've got TS compared to ZY. And RS to XY. There's our statement of proportionality. All three sides in this case are in proportion, and you're all set. Next diagram. Determine whether the two polygons are similar. If they are, write a similarity statement and find the scale factor of ABC to DEF. So they've already got all this notation in there for you. You have to make sense of it. They are telling us that it's up to us to figure out if these are similar or not. They didn't give us that information. It's up to us. So we have to realize that we've got to talk about the corresponding angles, and they have to be the same. So it's really just a matching game. 1 arc to 1 arc, 2 arcs to 2, and 3 to 3. So let's start with angle A. Angle A would correspond and be congruent to angle D. I know this because of the arcs. This is not a guessing game. It's an absolute, it's a definite, it's for sure. Then we've got angle B congruent to angle E, and angle C congruent to angle F. We know that because of the arcs. So therefore, we got our corresponding angles congruent, very important. And now all that's left is our sides. We have to see that our sides are in proportion or not. And how do we do that? Well, you literally set up your proportions. So we want to see how they went from ABC to DEF. So you just start at a side length and you match it up to its corresponding side. So for example, if I pick the side length of 20, all right, that's the side length that compares the 1 arc to the 2. So the side that represents the 20, if I shrank it, would be the 10. So 20 needs to correspond to 10. It needs to find our scale factor. 20 over 10 can be reduced by 10, and you just get 2 over 1. Now, I have my triangle DEF up in the numerator, so I need to keep with the same pattern. If I want to go to the next side, I've got 12 over 6, which also reduces to 2 over 1. And then my last side would be 14 over 7, which is 2 over 1. Since they all have the same ratio of 2 to 1, they're all in proportion. Since my corresponding angles are congruent, this is definitely similar. So if we want to write our statement of proportionality, you just connect your side lengths. So we have DE was to AB, as EF was to BC, and DF was to AF. And the last thing that you can do with similar figures is you can actually find missing side lengths. But what's important is that they have to tell you that the figures are similar. It's the only way you can't assume anything. So they're telling you already that this triangle is similar to this triangle, so your corresponding angles are the same, and there has to be a ratio that exists between the two triangles and the side lengths. How did one get to be the other? It's not just random. It has to be a scale factor. So the way you do it is by setting up your proportion. You're going to take two of the ratios and you're going to set them equal because they have to be the same. Just like in example 2, they all had the scale factor of 2/1. All right, this is the same case. So there's lots of ways to set up your proportions. I'm going to stick to kind of the same pattern. So I'm going to say that side length ST, which was 4, corresponds to side length of 6. All right, this is the left side, this is the left side. That has to be the exact same proportion as X is to 14. Now, hopefully everybody is saying to themselves, well, now you just have two fractions set equal, and if you have two fractions set equal, all you have to do is cross multiply. So you're going to get 6x equals 4 times 14. You could reduce the 4 6 down if you wanted to. That would be up to you. You get 6x equals 56. They're connected by multiplication, so all you have to do is a little division. And you get 9 1/3, or 9.3 with the bar over it. All right, so that would be the side length, the missing hypotenuse. Now that's all there is to it. We're going to elaborate on it a little bit in class, but if you have any questions on ratios or proportions, make sure you ask, and we're going to practice in class.